Okay, so hi all. Uh, this is tutorial 13. This will be the last tutorial for this course Quantum Mechanics 1. And before we begin, do you have any doubts of your own that you want to discuss? Okay, so then let's start with some problems. So today the problems that we'll be solving will be a kind of cumulative problems for all the weeks that we have solved before and not based on any particular topics. So let me quickly write down the first problem. So here it is. The first problem is so we have given a potential and then we are asked what will be the first excited state energy, and these are our options. So 2h cut omega, 3h cut omega, 3 by 2h cut omega, or 5 by 2 h cut omega. Okay, so this is the problem. Now the first thing that we can see clearly, like this potential is kind of resembling the harmonic oscillator potential, right? So let us rewrite our potential. Our potential is, now the first term we can write like this, and the second term we can write like this. Now this, now for the second term, what we can do is we can rewrite this second term as follows. We can write, instead of omega we can write 2 omega. Okay, so it's half m 2 omega whole squared and y squared. So this 2 omega term then takes care of this 4. So our total potential will then become this thing. Okay, so now basically what we have done is we have reduced our problem as a sum of two harmonic oscillator potentials, right? So this is simple harmonic oscillator with frequency omega, and this is another simple harmonic oscillator with frequency 2 omega, right? So if we want to now write our energy E, that we can write as, so our energy E will be, for this case it will be nx plus half h cut omega, and because of the second term we will get ny plus half h cut and then 2 omega. Okay, so we can write it as nx plus half plus ny plus half into 2 and h cut omega. So this is our energy. Now the question is asking for the first excited state energy. So for ground state, for ground state, our nx and ny both will be 0. So our ground state energy E0 will be half plus 1 h cut omega, which will be equals to 3 by 2 h cut omega. Now for first excited state, our nx will be 1 and ny will be 0. This will give us E1 as 1 plus 1 by 2 plus 0 plus 1 by 2, which is simply this, plus 1 h cut omega. So this is 3 by 2 plus 1, which is 5 by 2. So 5 by 2 h cut omega, which means option D. Now one question that might come to our mind is, why didn't we take, what about this condition that nx is 0 and ny is 1? So as we will see, if we put this thing in our energy equation, so we'll get, what the energy that we will get is 0 plus half plus 1 plus half into 2 h cut omega. So this will be half plus 3 by 2 plus 3 h cut omega. So this will be 7 by 2 h cut omega. So you can see that when we substituted nx equals to 1, so this condition basically nx equal to 1 and ny equal to 0, we got 5 by 2 h cut omega. But if we put nx as 0 and ny as 1, then we get 7 by 2 h cut omega, which is higher than the other. So this will be our second excited state energy. Okay, so now we are very confident that this is the first excited state energy. Okay. So let's do the next one. So let me write down the second problem. Okay. Let 0 and 1, okay, let me write it down. Okay, so we are given a one-dimensional simple harmonic oscillator SHO, and then we are asked to find delta p for a given state 1 by root 2 0 plus 1, where 0 and 1 denote the normalized eigenstates. So our options are as follows: under root h cut m omega by 2. Option B is under root h cut m omega by 2, under root h cut m omega, and option D is under root 2 h cut m omega. Okay, so these are the options which are given to us. Now, first of all, we need to define what this delta p is and how do we find out this delta p. So we know that delta p is defined as the under root of p squared minus p squared. Therefore, to find out the value of delta p, we must find out the expectation values of p and p squared. So let's start with p first. Now, momentum for a simple harmonic oscillator can be written in terms of the raising and lowering operators by this equation. Right, where this a dagger is the raising operator and a is the lowering operator. Okay, so this is p and our psi is given to us as 0 plus 1, so 1 by root 2 0 plus 1. Now if we do a dagger psi, we will get 1 by root 2, and then this will become under root 1 times 1, and this will become under root 2 times 2. This is because a dagger on nth state, this gives us under root n plus 1 and the n plus 1 state. Okay, so 0 becomes 1 and 1 becomes 2. If we had n, we would have gotten n plus 1. Similarly, a psi, so we will have, because this state is already 0, which is the lowest state, we cannot reduce it further, so first term will be simply 0, and second, so this is 1, so we will get under root 1 and 0. Okay, now this is because a on n gives us under root n and n minus 1 state. Okay, so 0 becomes just 0 and state 1 becomes state 0. Good, so now the expectation value of our momentum p, this value becomes m h cut omega by 2 psi a dagger minus a psi, right? And then if we do this operation, so basically we can see that here we have states 1 and 2 when we do a dagger, right? And our psi is this state. So basically this psi a dagger psi will give us, okay, let me write down. So we'll have iota m h cut omega by 2. We'll have psi a dagger psi minus psi a psi, right? So now we can see when we have this a dagger psi, so we have state 1 and state 2, and for psi we have state 0 and state 1. So this state 1 and this state 1, they will be the only terms corresponding to some non-zero values, right? And so this is 1 by root 2 and 1 by root 2, which is their prefactors. So this term, this first term will give us m h cut omega by 2, and this will give us 1 by root 2, 1 by root 2. Okay, and the remaining terms will be 0. Similarly, for psi times a psi, here we only have the 0th term with a prefactor of 1 by root 2, and here again we have 1 by root 2. So we'll have minus 1 by root 2 times 1 by root 2. So this is half minus half, so this entire term is 0. Therefore, expectation value of P is 0. Okay. So now, what about P squared? Now P squared will become, this iota squared becomes minus, and the under root goes over. So we have m omega h cut by 2. And here we have, you can see, a dagger minus a squared. So a dagger minus a squared. So this we can then write down as by 2 a dagger squared plus a squared plus a dagger a, sorry, not plus but minus, minus a dagger a and minus a dagger. Okay, and now we know this we can further simplify to the number operator as a dagger squared plus a squared minus 2n plus 1, where this n is nothing but the number operator. So this is our p squared. Okay, now to find out the expectation value of p squared, we can straight away write this as expectation value of a dagger squared plus expectation value of a squared and minus 2n plus 1 expectation value. Now these two terms, as we have seen, so this a dagger squared expectation value will be 0, and similarly a square expectation value will be 0. Because why? Because this will raise our psi 2 times, right? So this 0th state will become 2 and this state will become 3. So a square, basically a dagger square, will give us a 2 and 3 state. And if we then take bra of psi and do this thing, right? So you can see here on the right side we have 2, 3, but on the left side we have 0 and 1. And because of the orthogonality, we will get 0. Okay, similarly for the reducing operator, we get 0. And finally, for p squared, expectation value, this minus minus now becomes plus. what we are left with is the expectation value 2n plus 1. Okay. So yes. So what now we have, so our psi is in 0th and the first state with equal probability. Okay, let me again write down our psi. So it is 1 by root 2, 0 plus 1, right? So then the expectation value of the number operator n, so our basically our n will be simply it will be 1 by root 2 into 0, right? So basically it will give me, sorry, not 1 by root 2, but 1 by 2 into 0 plus 1 by 2 into 1, right? This will be the expectation value, that there is half of a probability for it to be in the 0th state and half probability for it to be in the first state. So this term is 0 and so we simply get half. So our n is half, therefore our p squared becomes m omega h cut by 2, 2 into 1 by 2 plus 1. Okay, so this is simply 2. So this is simply m omega h cut. And finally, we can write our delta p, which we defined earlier as this thing. This will then be nothing but m omega h cut. So option C. Hmm. Okay. Okay, so that was simple harmonic oscillators. I did a couple of problems. Now let's do one problem regarding the rotation of spins. Okay, so we studied rotational groups. Let's do a problem. Okay, so we have system of spin half particles and that is prepared to be in the eigenstate of sigma z with eigenvalue plus 1. Okay, so eigenvalue of the spins is plus 1. Then what we do, we rotate the system. The system is rotated at an angle of 60 degree about x-axis. So the rotation happens about x-axis and the problem is now the fraction of particles that will be in the plus one eigenstate of sigma z will be. And so our options are 1 by 3, 2 by 3, 1 by 4, 3 by 4. Okay. So right. So we have a system of spin-off particles, and sigma z is having eigenvalue 1. So if we think of these particles in terms of their spins, it would mean that all the particles in the system are having a plus 1 spin, right? So all of the particles are spin up particles. Now the system is rotated at an angle of 60 degrees about x-axis. So the question is that what will be the fraction of particles that will now be in the up spin. Okay, so we now need to find out. So initially, basically, then what we can do is we can define our wave function. Okay, so initially our wave function, so we can define our initial wave functions to be simply 1 0, right? Because if we now operate our sigma z, so we'll get eigenvalue 1. And now the rotation rx about x-axis theta we know is written like this. So we have cos theta by 2 iota sine theta by 2 minus iota sine theta by 2 and cos theta by 2. So this is a unitary transformation, and here theta is given as 60. So basically what this then becomes is theta by 2 becomes 30. So this becomes root 3 by 2 iota by 2 minus iota by 2 and root 3 by 2. So this is our rotation matrix. So our final state psi of theta will be the operation of this rotation matrix or the rotation operator on our initial state, which was 1 0, right? So we will have under root 3 by 2 iota by 2 minus iota by 2 and root 3 by 2, and here we have 1 0. So our psi then becomes, this will give us under root 3 by 2 and this will give us minus iota by 2. So this is our psi. Now if I want to write in terms of the our orthogonal sigma z eigenkets, so this is one of the eigenket, other eigenket corresponding to the eigenvalue. So this have eigenvalue sigma z eigenvalue as sigma z eigenvalue for this eigenstate will be -1, and for this it is +1, right? So if I want to now write this final state psi in terms of the other two states, I can simply write it as under root 3 by 2, 1, 0, and minus iota by 2, 0, 1. Okay, now clearly the probability of the spin up particles will be corresponding to this first term, and the probability corresponding to the spin down particles will be the one corresponding to the second term. Right? So the plus 1 for plus 1 eigenvalue, the probability will be the square of under root 3 by 2, which will be 3 by 4. And for minus 1, the probability will be mod this. So iota by 2 will give us probability as 1 by 4. Right. So what is the fraction? So 3/4. This is the probability that we are getting for plus 1. So the correct answer is D. Okay. Okay, so let's do the next one. So we have an electron in a hydrogen atom, and we are measuring its position, right? So the question is then, what will be the probability that it will be found at a distance r greater than equal to a naught, where this a naught is the Bohr radius. So for option A we have 0.91, for option B we have 0.66, here we have 0.32, and then here we have 0.13. Okay. So for the ground state, we know that the radial part of the wave function, so if this is our distance r, and let's say this is a naught, which is the Bohr radius, we know that the, okay, let's call that, this is the radial part of the wave function. We know that the radial part reaches its maxima at a naught, and then decays and ultimately goes to 0 at infinity, right? So this is like the function. Now the question is asking the probability for r greater than equals to a naught. So basically this region. That what is the probability that our electron is in this region? That is the question. Okay, so we can write that our probability P defined in this region a naught r infinity, this we can write as limit a naught to infinity r squared mod of r 10, which is the ground state, and dr. Okay, and we know that this r10 is nothing but 2 by a naught 3 by 2. Therefore, our probability becomes 4 by a naught cube a naught infinity r squared e to the minus 2r by a naught dr. And here we will also have e to the minus r by a naught. Okay, so this is what we have now. So now what we can do is basically apply integration by parts. So let's say this is, let's call this integral I. Let I is equals to okay, then basically we can write it as r squared, and integrating this term we'll get this same term e to the minus 2r by a naught, right, and multiplied by so this is e to the minus 2r by a naught, so multiplied by minus a naught by 2. So this thing with limits a naught and infinity, right, and then for the second term we'll have 1 minus, and differentiation of r squared will give us 2r, so integral r, and then the same term minus 2r by a naught, and so here we will have minus a naught by 2, so 2 and 2 will cancel and this will become plus, and instead of 2 we can just write a naught here. Okay, so we will have this term. So now if we put this limit infinity, so this term goes to 0, so only the a naught term remains. So our I then becomes this minus minus will become plus, so a naught by 2 into a naught squared e to the minus 2 a naught by a naught, so e to the minus 2. Okay, and then plus, so again this term will give us a naught times, so this will give us r e to the minus 2r by a naught, and then multiply this thing by minus a0 by 2, right? And then put the limit here again from a0 to infinity. And then we'll have minus, so this will then again become plus a0 by 2 integral e to the minus 2r by a0 dr, a0 infinity. Okay, so our I then becomes a0 cube by 2 e minus 2 plus a0, and here again putting infinity will just give us 0. So this again, here we'll have this a0, putting a0 again e minus 2. So a0, and this will make it minus, so minus a0 squared over 2 e minus 2 plus a0 squared over 2, and this integral will give us this thing. So the only term that will remain is, let me just write it down, e to the minus 2r by a0 and minus a0 by 2. Okay, so basically these two terms will just cancel out, and what we'll have is a0 cubed minus a0 cubed over 4, and e to the power minus infinity is 0, and then minus minus becomes plus, so e to the power minus 2. Okay, this is then what we have. This is I, and then we have to multiply this thing by 4 by a0 cube to get our probability. So our probability P is 4 by a0 cubed multiplied by a0 cube over 4 e minus 2, or 1 over e squared. Let's write as 4e squared. So this 4 and this cancel out, and let's find out the value of 1 over e squared. So the probability finally that we get is 0.66. Option B. Okay, so let's do next one. We have 3 identical spin half particles of mass m, which are confined to a one-dimensional box of length L, assuming that they are non-interacting, the energies of the lowest two eigenstates in units of pi squared h cut squared over 2ml squared are 3 and 6, 6 and 9, 6 and 11, 3 and 9. Okay, so we have three identical spin half particles. Now we know because they are spin half, so each energy level can be occupied by 2s plus 1, which is 2 into half plus 1, which is equals to 2. So the degeneracy is 2. So at max, two particles can be there in the same energy level. Okay. So if these are our energy levels, this corresponds to n is equals to 1, 2, 3, 4, so on. So here we have, for the lowest possible spin configuration, lowest possible energy configuration, we'll have two particles here and then one particle here. Now for the next energy state, we'll have one particle here and two particles here. Okay, so this is, let's say, the ground state, and this will be the first excited state. Okay, so for ground state, our total energy E will be, so n squared is 1 squared plus 1 squared and then plus 2 squared, this thing multiplied by pi squared h cut squared over 2ml squared, which will give us 6 times this number. Okay, and for the first excited state, our energy will be 1 squared plus 2 squared plus 2 squared. So this is 9, because 1 plus 4 times this quantity, pi squared h cut squared by 2ml squared. Okay, so, and that is what we are asked to find, right? The energies of the lowest two eigenstates. So we can clearly see that the energies are 6 times this thing and 9 times this thing. So option number 2. So option B, 6 and 9. So let me write for a hydrogen atom, we are given a wave function psi 1 by root 6 phi 200 plus under root 2 by 3 phi 1 minus 1 and minus 1 by root 6 phi 100. Okay, where phi n l m are the Hamiltonian eigenstates. Okay, so this is the standard notation, and now we are asked the expectation value of the energy E is, and our options are minus 10.8 EV, minus 6.2 EV, minus 9.5 EV, or D minus 5.1 EV. Okay, so now we have a wave function which is written in as a linear combination of three eigenstates, right? So our wave function is a combination of phi 200, phi 1 minus 1, and phi 10, with all with different prefactors, right? 1 by root 6, root 3 by 3, or 1 by root 6. So first of all, let us check if the wave function psi of r, which is given to us, is normalized. So how to check that? So we take the square of the prefactors and add them. So 1 by 2, 1 by 6, plus 2 by 3, plus 1 by 6. So this thing we can write as 4 by 6. And clearly we can see that this sum is coming to be 1, which implies that psi is normalized. So now we don't have to worry about the normalization factor. Wave function is already in the normalized form. Now second thing is that these phi, they have these subscripts, right? So here you can see 200, 2, 1 minus 1, and 100. Now these subscripts here you can see corresponds to the eigenvalues of n, l, and m. Now for energy, we know energy depends only on the n eigenvalue. So energy is given as minus 13.6 by n squared, right? And EV. Okay, so this is the En. So energy in the nth state is given by this equation, where n goes from 1 to 3 and so on. Okay, so here we can see that here n is 2. So you can see n is 2, again n is 2, and here n is 1. Okay, so for n is equals to 1, E1 is simply minus 13.6 EV, and for n is equals to 2, we have minus 13.6 divided by 4, which should give us minus 3.4 EV. Right, for that, yeah. Okay. Now this is the thing. So and now we, but all of, so for having probability, so for having this energy E1, probability is 1 by 6. Therefore the expectation value E, we can write as 1 by 6 times minus 13.6 plus, and for the n is equals to 2, here we have 4 by 6 and here we have 1 by 6, so total 5 by 6, so plus 5 by 6 into minus 3.4. So this is the expectation of value of energy that we will get. So let's take this 1 by 6 thing outside. Let's take the minus sign also outside. So this will be 13.6 plus 3.4 is 17, right? And if we add them, we'll get 30.6 minus 30.6 divided by 6 EV. So which will be roughly 5 EV, right? Slightly more than 5 EV. And which means option D, right? Option D, which is 5.1 EV. Yeah. Yeah. Correct. So our E is 5.1 EV. Okay, let's do the next one. So which one was it? 7th. Okay. So find the ground state energy for the potential in units of h cut omega, and our options are 5 by 2, 7 by 2, 3 by 2, and 1 by 2. Okay, so if we look at the potential, like we have already solved one problem like this, we know we have to convert it to the form of half m x square and put rest all the things in terms of omega, right? So we will rewrite our potential as half m omega squared x squared plus half m 2 omega squared y squared plus half m 4 omega squared z squared, right? Because 4 square will give us 16 and dividing it by 2 will give us 8. Similarly, this will give us 4 by 2, which is 2. So all things are okay, just some basic arithmetic we have done. Now the energy we can write as nx plus half h cut omega plus ny plus half 2 h cut omega plus nz plus half 4 h cut omega. And in terms of h cut omega, if we take that as common factor outside, we can write as nx plus half plus 2ny plus 1, okay, and plus 4 nz plus 2. So this is the energy that we have. Now for ground state, put all of the n's to 0. So here we will have h cut omega, and this will be just half plus 1 plus 2. So this is 3 plus half h cut omega, which is nothing but 7 by 2 h cut omega, which means option B. Okay, let's do the next one. So at t is equals to 0, psi is given as under root 2 by L sine pi x over L minus sine 3 pi x over L. For a particle confined between x equals to 0 and L. Okay, so its wave function at some time t is equals to ml squared by 4 pi h cut is, and our options are under root 2 by L sine pi x by L minus sine 3 pi x by L e to the power iota pi by 6 under root 2 by L sine pi x by L minus sine 3 pi x by L e to the power minus iota pi by 8 . Okay, so these are the 4 options. Now this is the initial wave function at time t is equals to 0. and we can see it is written in terms of two sine functions. Okay, so basically we can rewrite our initial wave function, which is psi x at time t equals to 0. We can rewrite as under root 2 by L sine pi x by L minus under root 2 by L sine 3 pi x by L. Okay, now this we know, so our psi at t equals to 0 is nothing but phi 1 minus phi 3. Right, so the ground state and the second excited state, or the first state and the third state. Right, okay, so our psi for some later time t we know is then given as e to the minus iota et over h cut. So here we will have e1 and then minus phi 3 e to the minus iota. Now here we will have e3 t by h cut. Okay, where e1 we know is simply pi squared h cut squared over 2 ml squared, and e3 is 9 pi squared h cut squared over 2 ml squared. Also time t that is given to us in the problem is ml squared over 4 pi h cut. Right, so then if I wanted to write t over h cut, so this becomes h cut squared. Okay, so then all these ml squares will get cancelled, and then let's see what we get. So finally we can write our psi as, so psi at some x comma t will be phi 1 e to the minus iota. Now e1 is this thing, and multiply this by t by h cut. So ml squares gets cancelled out, h cut squared gets cancelled out, 1 pi gets cancelled out. So what will be left with is e to the minus pi iota and pi over 8. And for the other term we will be left with e to the minus iota 9 pi by 8. Okay, so now if I take this, if I take this e to the minus iota pi by 8 factor outside, inside I have phi 1 minus phi 3 multiplied by e to the minus iota pi. Okay, so now we know this e to the iota theta is cos theta plus I sin theta, and if we put theta as minus pi, which is 180, so this will give cos of 180, which is minus 1, so this becomes plus. So this then simply becomes this quantity. Phi 1 plus phi 3. Or I can write it as e to the minus iota pi by 8 under root 2 by L sine pi x over L plus under root 2 by L sine 3 pi x over L. So option C. Okay. So this was question number 8. Let's do question 9. So we have particle of mass m is confined in a 3D box Vxyz is equals to 0, infinity, 0, okay, so we have a cubic potential, right? So we have a 3-dimensional box and a particle is confined within that box. Outside the potential is infinity. So the problem is the number of eigenstates of Hamiltonian with energy 9 pi squared h cut squared over 2m a squared is 1, 6, 3 or 4. Okay, so this is the question. So now we know for a 3-dimensional box, so our energy nx, ny, nz will be nx squared plus ny squared plus nz squared pi squared h cut squared over 2m a squared. And now this factor is coming out to be 9, right? So let's see. So we have nx, ny, nz, and then let's say here let's find out what will be the value of nx squared plus ny squared plus nz squared. So let's make a table, right, where we have all these things. And then let's calculate. So for, okay, let me just check. Okay, so when all of them are 1, so this is 3. For this kind of configuration, so this will give us 4, 5, 6, right? And for this type of configuration we are getting 9. And now there are 3 ways to get this as 9. Okay, and those 3 ways are, so put 1 here, 2 here, sorry, and then put 1 here and 2 here, so 9, 9. And then there are no other ways to get 9, so total we have 3 ways. Okay, and that is what the question is asking. So the number of eigenstates of Hamiltonian with the energy is C. So these are the 3 eigenstates. So this is the first eigenstate for nx2, ny2 and nz0. This is the second eigenstate and this is the third eigenstate. So we have 3 eigenstates. Okay. Good. So this was 9. Let's do 10. So consider an operator alpha then the commutator alpha comma cos x is, and the options are minus sin x, cos x, minus cos x, 0. Okay, so this commutator between alpha and cos x, let's write down alpha as x plus dy dx, and the second term is just cos x. So then we can break this into two commutators, x cos x and dy dx cos x, right? So this first commutator will give us simply 0, because this is like the commutator of x and f of x, so this commutator just goes to 0, and the second commutator is non-zero. And let's find out what this second commutator is. So if we operate this commutator on some dummy wave function, let's say psi of x, so we will get d by dx cos x psi x, right, and minus cos x d psi over dx, right? So this will give us cos x d psi over dx, right, plus psi x dy dx of cos x, and minus cos x d psi over dx. So these two terms cancel out, and then basically what we get is d by dx comma cos x psi of x just gives us so minus sin x psi x, right, because differentiating cos gives us minus sin. Therefore, and this commutator is nothing but this commutator alpha cos x, so alpha cos x is nothing but minus sin x, which means option A. Okay. So let's do the 11th one. If Lx, Ly, Lz are the angular momentum operators. Okay, then the commutator Lx comma Lx Ly Lz, may be simplified to iota h cut Lx Lz squared minus Ly squared iota h cut Lx 2 Lz squared minus Ly squared Lz Ly Lx or 0. Okay, so let's have a look at this commutator. We have Lx and Lx Ly Lz. So we can, using the product rule, firstly we can write this as Ly Lz plus Lx comma Lx Ly Lz. Now this second commutator goes to 0, right? Because this is Lx Lx. So we have already simplified this one to this smaller commutator. And then again using the product rule, we can write this as Lx comma Ly Lz plus Lx Ly Lx comma Lz. Okay, now using the cyclic commutation, we know that this just becomes iota h cut Lz. So this becomes Lx and iota h cut Lz and Lz, and Lx Lz will give us Ly. So this becomes Lx Ly and minus iota h cut Ly. Okay, so this then we can write as iota h cut Lx Lz squared minus iota h cut Lx Ly squared, right? So now let's take this iota h cut Lx as a common factor, and inside we will have Lz squared minus Ly squared, which is option A. Okay. So let's do Next one, this will be, I think, 12. So the 12th problem for today. Again, we have a particle of mass m in one-dimensional rigid box in the interval 0 to L. So for particle of mass m in a 1D box between x is equals to 0 and L, the wave function is given as psi x is equals to under root 2 by L (3 over 5) sine 2 pi x over L plus 4 over 5 sine 4 pi x over L. Okay, this is the wave function. Okay, so find out the possible outcomes of energy measurements okay, and the average value of energy. Okay, and this one does not have options, so let's straight away get into solving this one. Now if we look at the wave function, first of all, is it normalized? For a 1D box, we know that phi n is given as under root 2 over L sine n pi x by L, right? So this is phi n. So if I want to rewrite my psi, I can rewrite my psi as 3 by 5 and here n is 2. So phi 2 plus 4 by 5, phi 4. Okay. Now these phi's are orthonormal. So these are orthonormal sets. Okay. And therefore, if I do psi squared, I'll have 3 by 5 squared plus 4 by 5 squared, which is 1. So this is psi is normalized. Good. So here, so energy corresponding to phi 2 will be E2, and that n squared will be 4 pi squared h cut squared over 2 m L squared, and E4 will be 16 pi squared h cut squared over 2 m L squared. So the energies that we will be measuring, to simplify, these two energies will be measured. So this one will be simply 2 pi squared h cut squared over ml squared, and E4 will be 8 pi squared h cut squared over ml squared. Okay, so we'll be measuring these two energies. Now the average, the second part is, so first is the possible outcomes. These are the two possible outcomes, and the second part is the average value of energy. So to find out the average value of energy, So, or the expectation, we need to do P2E2 plus P4E4, where this P stands for probability. Okay, so this will be 3 over 5 squared, which means 9 over 25 into 2 pi squared h cut squared over ml squared, and this will be 16 over 25 into 8 pi squared h cut squared over ml squared. So let's take all these things outside. So this becomes pi squared h cut squared over 25 ml squared. And inside we have, this is 18 and this is 8 and 130 and 128. Yeah. Okay, so 128 plus 18 will give us 6 and 4. 146 over 25 pi squared h cut squared over ml squared, right? So this is the average value of energy which we will be getting. Okay, cool. So let's do, this was 12, let's do 30. So we are given for a simple harmonic oscillator, A is under root m omega by 2h cut and x plus iota p by m omega. This is the lowering operator. Then dA, sorry, then dA by dt is given by, and our options are a omega a minus iota omega a, omega a dagger, or iota omega a dagger. Okay, so whenever we want to find the time dependence in Heisenberg picture, we know we have this equation of motion dA by dt 1 over iota h cut a comma h plus del a del t. Now there is no direct time dependence, so this term directly goes to 0, and we can write our dA by dt as 1 over iota h cut, and this a is under root m omega by 2 h cut, that also we can bring outside. And inside we have x plus iota p by m omega, So this is A and it's by H. Okay, this is what we have. So for H also, for H, because this is a simple harmonic oscillator, so for H what we can do, we can write H as p squared over 2m plus half m omega squared x squared. Okay, we can use this Hamiltonian. So then this dA by dt, we will get 1 by iota h cut omega under root m omega by 2 h cut, and then here we will have x comma p squared by 2m, right, this term, right, and plus, so here we will have iota by m omega, and inside we will have p comma x squared, right, and this half m omega squared, let me write outside, so m omega squared and half, like this. So we'll have these two terms. Okay, so 1 by iota h cut under root m omega by 2 h cut. Yes. So then this becomes, then so this m will cancel, so this becomes iota omega by 2, this term, and this first term, so x comma, so we know that the commutator of x comma p is iota h cut, right, so this then becomes iota h cut and 2p over 2m. Okay, so 2 because of this squared, so we will have 2 iota h cut, and then this second term will give us iota omega by 2 and p comma x squared, so this will give me again 2 iota h cut, but with a minus sign, so minus 2 iota h cut and x, this quantity. Okay, so we can cancel out these iota h cuts, and let's keep this term as it is, and so here we have p over m and then minus iota omega x. Okay, now if I want to compare it with this term, I have this x as a separate quantity, so let me take out this minus iota omega outside, and then here I have m omega by 2 h cut, and then now I can write x here, and then plus p over m omega iota m omega, and if I want to write, I can write it like this, minus iota p over m omega, right, like exactly this form. Okay, x plus iota p by m omega, such that when I multiply this thing, this iota and iota gives me minus 1, so this minus minus becomes plus. Okay, good. Now this entire thing is nothing but the lowering operator A. So I can simply write it as minus iota omega A, and this is my dA by dt, which is option B. Okay. So let's do one last problem for today. Okay, that will be 14. Okay, so we have a particle in the infinite square well potential. Again, this is 0 or infinity. Okay, and then this particle is prepared in a state with the wave function psi of x so we have sine cube. Okay, this is sine cube pi x over a or 0. Otherwise. Okay, and the question is the expectation value of the energy is okay. Our options are okay. So this is the problem. Again, we have a 1D box, and the wave function this time is given as a sine cubed, and then we are required to find out the expectation value of the energy. So generally we know that for a 1D box the phi n's are of the form under root 2 by a sine n pi x over a. So linear sine, right? We don't have square of sine or cube of sine or something. So what we need to do, we need to use this identity, and we know that sine of 3 theta is 3 sine theta minus 4 sine cubed theta, right? So we'll use this identity, and then we can convert this sine cube to linear sines, which will be sine theta and sine 3 theta. Okay, so this would imply that sine cubed theta will give us 3 by 4 sine theta minus 1 by 4 sine 3 theta. Okay, therefore the wave function that is given to us, this a sine cube pi x by a, we can write a sine cube pi x by a. We can write it as a into 3a by 4 sine pi x over a, and minus a by 4 sine 3 pi x over a. Okay, so now we have this in terms of our phi n's. Okay, now we can find out what this a is. We just have to normalize. So normalization condition is this. So this implies that this 9a square over okay, no, before that let's write it in terms of the phi n. Okay, so now we can write our psi of x as, let's take out this a by 4 outside, and then we can write under root a by 2 into under root 2 by a into 3 sine pi x over a minus under root a by 2 under root 2 by a sine 3 pi x over a. Okay, which means we can write our psi of x as a by 4 and then 3 times under root a by 2. Okay, yeah, under 3 times under root a by 2 phi 1, and this will be minus under root a by 2 phi 3. Okay, now let's do normalization. So psi equals to 1, and this would imply that 9, and this will give me a, and 16 and 32, 9 a by 32 a squared plus a by 32 a squared. So adding this 9a squared plus 10a squared a by 32, so this is 1. So this implies that 10a by 32 a squared is 1, and this implies that a is under root 32 by 10a. So finally, my wave function psi of x I can write as 1 by 4 3 under root a by 2 under root 32 by 10a phi 1, this 1 by 4 is outside, minus under root a by 2 under root 32 by 10a phi 3. So my psi of x is, upon simplifying, gives me 3 by root 10 phi 1 plus 1 by root 10 phi 3. Okay, this is my normalized wave function. Now once we have normalized and we know that the corresponding energy E1 is pi squared h squared over 2 m a squared, while E3 will be 9 pi squared h squared over 2 m a squared. So the expectation value of energy E will be 3 over under root 10 squared pi squared h squared over 2 m a squared plus 1 over 10 squared 9 pi squared h squared over 2 m a squared. Okay, so which means that this is 9 by 10, and this again, this is also, this is 1 by 10, and this is also then 9 by 10. Okay, so basically 2 into 9 by 10 into pi squared h squared over 2 m a squared. So these two will cancel out, and finally our expectation value will be 9 pi squared h squared over 10 m a squared. And let's see if we have such an option. We have option C, which is the correct answer. So yeah, that's more or less it. Okay, I guess it's already time. So, and yeah, this was the last tutorial session. I hope these problems will help you in understanding these some concepts of quantum mechanics. So with that, let me end the meeting. Have a good day ahead. Bye bye.